Okay, from radioactivity topic, we have this numerical. A radioactive material is being produced at a constant rate x. Half-life of radioactive material is y. This is half-life. After some time, the number of radioactive nuclei become constant. What is value of this constant? And there are four options. In radioactivity, what happens? So, there is a parent nuclei. There is disintegration. After disintegration, a daughter nuclei is produced. This daughter nuclei is maybe again a radioactive material and it is disintegrate further. So, here there is disintegration, there are radiations. There is a particular rate at which these nuclei are being disintegrated and it is given to us. This is being produced at a constant rate x. These are being produced, not this. This is a parent nuclei, there is disintegration and these are being produced. At what rate? The rate is x. These are being produced x per second. Okay. Half-life of radioactive substance. The radioactive substance which is produced has a half-life equal to y. For half-life we have a formula. This is log 2 upon disintegration constant, and this is for half-life. And here given half-life is y, so y is equal to log 2 upon lambda. Okay, so from here there is further disintegration and the rate of this disintegration is lambda. And what is this? We understand that if at any instant the number of particles are n, the number of radioactive nuclei are n, then disintegration is proportionate to n, or disintegration is equal to lambda into n. This is disintegration. The particles which are disintegrating is equal to delta into n. So if n are the particles here, then delta n are getting disintegrated every second. Now the condition, the number of radioactive nuclei become constant. That means this n should be a constant. This should not change. Why this will not change and why this will change? The answer is, it is being produced at the rate of x. It is being disintegrated at the rate of delta n. So if this is more than this, then they are finished. If this is less than this, then they will go on accumulating. They will go on integrating and this will become a larger quantity. They say it should neither increase nor it should decrease. What is the condition for that? That is the rate of disintegration. This rate, the rate of generation, should be equal to rate of disintegration. So rate of generation or production should be equal to rate of disintegration. So this is x and this rate of disintegration is delta n. Okay, but this delta we can translate into y. How we can translate it? Here is the relation, that half-life. Y is the half-life, y is log 2 upon lambda, so lambda is equal to, from here we get, this is log 2 upon y. So this lambda we will replace by log 2 upon y. So This is x is equal to, now we are trying to match it here. Why? The value of this constant. What is this constant? This constant means what? This constant means this number n. So we have to find the value of n. So lambda is replaced by this and this n we put here n. Now how much is n equal to? N is equal to x into y upon log 2. So let's check whether there is an option for this. Here is the option for this. So this is our correct option. See it once again. Here the number is constant. This number has to be constant. So what is the main point here? The rate of generation is equal to rate of disintegration. Disintegration formula we should remember. Other thing we should remember is half-life of substance is y. So we must remember half-life formula related to lambda, that is disintegration constant, because this disintegration is lambda into n. We are going to use lambda here. So in this way we could find the value of n, which is xy this. So this is the number of radioactive nuclei, and at this rate, given rate, if this condition is met out, then this will remain constant. Here is a numerical from radioactivity. I will read it with you. A radioactive substance is being produced at a constant rate 200 nuclei per second. The decay constant of substance is 1 per second. After what time the number of radioactive nuclei will become 100? Initially there are no nuclei present. Initially there were no nuclei. The nuclei are being produced. How they are being produced? There is a constant rate of 200 nuclei per second. That means there is a parent nuclei, which is producing this nuclei, and after disintegration these are being produced. How many are these being produced? At a constant rate of 200 per second. Okay. After that these are also getting decayed, and we know if there is a decay constant delta at a particular time, there are number of nuclei n present, then the nuclei being disintegrated per second is delta into n. This is disintegration per second. So delta n are getting disintegrated. So at the same second, in the same time period of 1 second, these many are produced because of it disintegration. These are produced and these are getting disintegrated. So every 1 second, how many are accumulating here? We know that every 1 second there is a accumulation of 200 minus delta n. This is accumulation every second. What do we call it? In mathematics, this is the rate of change, the rate of production per second. Initially, how many were there? Initially, there were no nuclei present. So in every 1 second, so much are added. So what we can tell it? What we can say that what is this mathematically? This is dN by dt. The rate of change of nuclei n. This is changing at the rate of 200 minus delta n. I hope it's clear now. 200 produced, delta n disintegrated. So there is a change of 200 minus delta n, dN by dt. Okay. Now what is our question? After what time t? After what time the number of radioactive nuclei, the number n, will become 100. So n is given to us, t we are supposed to find out. This is our relation. N is given to us, t we are supposed to find out. Then what will happen to delta? We go for searching and we find it is given. The decay constant is 1. So this is given to us. This we have to, this is also given to us, and this we are supposed to find. find out. So there is a mathematics involved. We can do that. This will become dn upon 200 minus delta n. This is equal to dt. Let's integrate on both sides. Integration. When it is 0 to t, these number will change from 0 to n. T is the time when the number become n. So this is 0 to n and this is 0 to t. Now this integration is to be done. So in mathematics we can do this integration. There are 4-5 steps that I am not going to do it now. I will simply write the result, and this result will be 200 upon lambda. If we solve these two, we will find that n is equal to 200 upon lambda 1 minus e to the power minus lambda t. This you can take help of your mathematics teacher, or if you are good in calculus, integration calculus, you can do it yourself. Otherwise, I will have to take some time and do it, but it's possible, it's easy. Okay, now once we have got it, we have to put the values and find the value of t. N is equal to 100. This is equal to 200. Lambda is equal to 1. So this is 1. This is 1 minus e to the power minus, again this is 1 into t. So this 200 will bring here 1 upon 2 is equal to 1 minus e to the power minus t. The next step, this one will come here, this will become minus half. So minus half is equal to minus e to the power minus t. So this is cancelled. E to the power minus t is 1 upon 2. So e to the power t is equal to 2. So t is equal to log 2. And I could not write the 4 options which are given. The 4 options which were given to us is, let me see. Okay, one is 1 second, 1 upon log 2, and third is log 2, and fourth is 2 seconds. And you have seen we got this result log 2. This is the right option. Okay, again I will repeat it. Radioactive substance being produced and it is getting decayed also. After what time the number will become 100. That means there is a process, something is being produced and the same thing is getting decayed. How much is the change? Produced minus decayed, minus disintegration. This is being produced every second, and for every second we have a notation dn by dt. The rate of change of this nuclei. Okay, so this is our equation. Now what is given to us? That this n will become 100 after some time and we have to find t. So this n is given, we have to find t. But here is dt, so to convert it into t, we have to integrate it. So this is our method of integration. Dt will go there and then we will do this integration. We get the right answer, log 2. Now we'll go for next question. Okay, here is another question from radioactivity. A radioactive material X decays into another radioactive substance Y. Initially only X was present. Delta X, delta Y, disintegration constants of X and Y. Nx and Ny are number of nuclei X and Y at any time t. Number of nuclei Ny will be maximum when either of these conditions is present. Read it once again. Okay. A radioactive material is X. Initially only X was present, there was no Y. Then this disintegrates and become Y. So X is the parent nuclei, Y is the daughter nuclei. the rate of disintegration from X is delta X. Okay, there is disintegration, this becomes Y. Y is again a radioactive material and there are disintegrations in Y also. The rate of disintegrated here is delta Y. Delta Y is the rate of disintegration here. At any instant, at any time t, these numbers are Nx and Ny. Ny. Okay, these are the numbers at any given instant. Now this Ny is being produced because of this reaction, and this is also disintegrating. This is decaying because of this disintegration. Now, what is the rate of production of Y? The answer is rate of production of Y is delta X Nx. How many nuclei are being lost per second? What is the rate of disintegration? That is delta Y Ny. So how many are the numbers produced? How it is changing? The rate of change of Ny is these are produced, these are disintegrated, this is the number increased per second. The number increasing per second, whose number? Ny. Ny is increasing per second by this rate. How we write it mathematically? This is rate of change of Ny. So this is rate of change of Ny given. Now what is being asked to us? The number of nuclei Ny will be maximum. When this Ny will be maximum? In calculus, in differential calculus, we have studied that this Ny in maxima and minima, that at maximum value Ny will be constant. At maximum value Ny is a constant. Therefore, d by dt of Ny must be 0. If this is 0, that means this is 0. Therefore, delta X Nx minus delta Y Ny is equal to 0, and you have solved it. Put it on this side. So what we get here is delta X Nx is equal to delta Y Ny. Let us check if there is any solution matching this. And we find it is here. So this is the right option. This is the condition, that delta Y Ny is equal to delta X Nx. When this thing has reached that the rate of production is equal to rate of disintegration, at that time this number will be maximum. Before that this number is less, after that this number will be less, but at that time this number will be maximum. So this is our answer for this. Okay, here is another numerical. Half-life of a radioactive substance A is 2 times half-life of another radioactive substance B. Initially, the number of nuclei of A and B are Na and Nb. After 3 half-lives of A, the number of nuclei of both become equal. Then what is the ratio? Na upon Nb initially. Okay, read it once again and notice. What do you notice? Radioactive substance half-life of A is 2 times the half-life of substance B. What does it mean? When A become half, then there are 2 half-lives of B. That means B will become half and further half. It will become 1/4 because 2 half-lives. Okay. Whose half-life is smaller? Answer is B has a smaller half-life, A has a larger half-life. Now it is given to us initially the numbers of Na and Nb, okay, 3 half-lives of A. when 3 half-lives of A have passed, what are the number remaining? A very easy method, remaining number of A, remaining nuclei of A after 3 half-life, after 3 half-lives. It was Na, half after 1 half-life, other half after 2nd half-life, other half after 3rd half-life. This initially you can remember and write it this way, power 3. Okay. So this will be how much? 1/8 of Na. This will become after 3 half-lives. Now, at the same time, Nb is getting disintegrated. If Nb is also getting disintegrated, what will be its new number? The initial number was Nb. We know that when there is 1 half-life of A, there are 2 half-lives of B. In that case, if there are 3 half-lives of A, how many half-lives will be there for B? The answer is there will be 6 half-lives, because that is double. So there will be 6 half-lives of B, and it will be half to the power 6. Half into half into half into half, 6 times 32. So this will be 1 upon 32. 64. Okay, 2 into 2 into 2 into 2 into 2 into 2. 2 to the 4, 2 the 8, 8 to the 16, 16 to the 32, 32 the 64. Okay, you are right, 64 of Nb. So this is what this become. Now what they say, what were initially Na and Nb we don't know, but after 3 half-life of Na, after 6 half-life of Nb, these two become equal. Both become equal. What both? A and B after 3 half-lives of A. Now we understand it that there are 3 half-lives of A, and according to this condition there will be 6 half-lives of B. It is already given twice. So after 6 half-lives this, after 3 half-lives of this, and now you can make both as equals. So Na upon 8 is equal to Nb upon 64, and you can find out Na upon Nb. Na upon Nb, you have already done it. 8 upon 64, that is 1 upon 8. Do we have an option? Yes, there is an option, 1 upon 8. So this is the right option. Okay. Okay, here is another numerical from modern physics. This is from the dual nature. An electron and a photon have same wavelength. Electron has wavelength, that is in its wave nature. Okay. If P is momentum of electron and E is energy of photon, the magnitude of P upon E in SI unit is either of these options. Okay. In dual nature, what we study, that electron travels in waves and photon has got material nature. It can have energy like an electron has. So in that case, we must understand that the formulas, the relations are same for electron as well as for photon. How? P is momentum of electron. What is momentum of electron? The formula for momentum of electron is same as formula for momentum of photon. And we all understand that momentum P has the relation h upon lambda. This we have studied in case of photon. The same is for electron because of the dual nature and because of the matter waves. Okay, now P is equal to h upon lambda, where lambda is wavelength of electron. Electron. P for electron. Okay, this is the relation for P. Now, energy of photon. Energy of photon. Energy is given by, we know it is equal to h nu. Nu is frequency. Okay, h nu is the energy, and this can be written as Planck's constant h. Nu we can write as c upon lambda. C is speed of light and lambda is wavelength. That is nu frequency. So frequency can be written as hc upon lambda, and this lambda is that of photon. C is speed of light. H is Planck's constant. Okay. Now P upon E. Let's do P upon E. This is equal to h upon lambda for electron divided by hc lambda for photon. So h upon lambda for electron into lambda for photon divided by hc, and it is given to us electron and photon have same wavelength. That means these two are same and can be cancelled. H is also cancelled. So what we get here, 1 upon C. 1 upon C is equal to 1 upon 3 into 10 to the power 8. This can be written as 10 upon 3 into 10 to the power minus 9. This is equal to 3.33 into 10 to the power minus 9. So if we match it, we have this option here. So this is our right answer for this question. See it once again. Next question is, let K1 be the maximum kinetic energy of photoelectron emitted by light of wavelength lambda 1. K2 maximum kinetic energy of wavelength lambda 2. If lambda 1 is equal to 2 lambda 2, then what will be the relation between K1 and K2? There are different options given to us. Which questions or which topic it belongs to? The answer is photoelectron emission. In photoelectron emission, we have studied about kinetic energy. So the first thing we must remember, what is the formula for kinetic energy? We all know that kinetic energy of a photoelectron is equal to energy of the photon, that is energy of the photon is h nu minus work function of that material. This gives the kinetic energy maximum. Okay, this we have done in theory. So kinetic energy is h nu minus omega or minus w. Okay, now we will fit this, we will put the values for different kinetic energies. K1 is the maximum kinetic energy emitted by light lambda 1. So this we can write as K1 is equal to h nu minus w. Now here lambda is given, wavelength is given, so we should use a formula which has lambda in it. So here we will change it and make it hc upon lambda. For K1 the wavelength is lambda 1, so we will write it lambda 1. Okay, so this is kinetic energy in the first case. Now for the second light, K2 is the maximum kinetic energy when the wavelength of photon is lambda 2. K2 is kinetic energy when wavelength is lambda 2. Again this formula. Okay, now we have to find relation of K1 and K2. There are many ways you can do. First, we have to use this equality. That is lambda 1 is equal to 2 lambda 2. That will make it easy for cancellations. So this lambda 1 can be put as 2 lambda 2. So this will be K1 is equal to hc upon 2 lambda 2 minus work function. Okay, it is like this. Now here we have to compare the two. We can use different methods, but I would like to use here, find the value of hc upon lambda 2 from this equation and put it here. So from this equation you see hc upon lambda 2 is equal to K2 plus W. That I will put here, Hc upon lambda 2, Hc upon lambda 2. So this will be K1 plus K2 plus W, K2 plus W upon Hc upon lambda 2, K2 plus W upon 2 minus W. This I will now solve. K1 is equal to K2 upon 2, separate it. So this will be plus W upon 2 minus W, and these two will make it K2 upon 2 minus W upon 2. This is equal to K1. Now we examine it. K1 is equal to K2 upon 2. Is it equal to? No. Decrease something from K2 upon 2, then K1 is equal to that. So which is bigger out of the two? See this inequality. Which is bigger? So the answer is K1. When something is decreased from this, then it is equal to K1. That means this is larger than K1. This is larger than K1, or K1 is smaller than K2 upon 2. That is why when we decrease something, then this become equal to K1. So this gives us the result that K1 is smaller than K2 upon 2. Why do we want it? Because our options are given that way. Here are the options: K1, K2, K1 to K, and there are two inequalities. K1 is less than K2 upon 2 and K1 is more than 2K2. So what we have find here is K1 is less than K2 upon 2, K1 is less than K2 upon 2. This is the right option. Okay. Yes, here is a question of binding energy. Binding energy per nucleon, 1 H2 and 2 helium-4 are 1.1 MeV and 7 MeV. 1 for this, 7 for helium. Okay. There is a process, hydrogen plus hydrogen, that is deuterium combined to make helium. Okay. Then how much energy is released? We know that in our binding energy curve, which was something like this, whenever a nucleon, there is a process of combining two small nucleus to make a larger nucleus. Then there is release of binding energy. Okay, how to calculate it? Let's write the process here. H. This makes 4. Okay. For hydrogen, the binding energy is 1.1 million electron volt per nucleon. How many nucleon are there? So answer, there are 2 nucleons. So how much binding energy on this side? So answer is binding energy is 1.1 into 2 plus in this, for this nucleus it is 1.1 into 2. Okay, this was the binding energy before combination or before fusion, you can say. After fusion, there are 4 nucleons and the energy is 7 million electron volt per nucleon. So after fusion, energy is, binding energy is 4 into 7. this is equal to 28 million electron volt. So the energy has increased, and we know when the energy increases, there is a fusion, energy increases. So this is the energy released. How much is the energy released? Therefore, energy released is equal to 28 minus, okay, let's solve this, 2.2, 2.2, this is 4.4. 28 minus 4.4, this is equal to 23.6 million electron volt. Do we have any option? Yes, here it is, 23.6 million electron volt. So this is a very simple, very basic question of binding energy. Okay, here next is a very peculiar question. A particle of mass 3m decays into two particles of mass m and 2m having non-zero velocities. That means they move. The ratio of de Broglie wavelength of particles, lambda 1 upon lambda 2. One has a wavelength lambda, the other has wavelength lambda 2. We know that whenever a material moves, it has a wavelength. It has wave's nature, it has material wave with it, and that material wave has a wavelength, and that is known as de Broglie's wavelength. Okay, the de Broglie wavelength is lambda 1 for the one, lambda 2 for the one, and we have to find out wavelength of the two. Okay, now a particle of mass 3m, this is 3m particle, and it breaks. By mechanics, by laws of motion, we know that the momentum before any action or process is equal to the momentum after the process. Here the process is explosion, decay. So before momentum before decay is equal to momentum after decay. Why I am thinking in this way? What is our thinking process for this? Why should I go for momentum at all? The answer is there lambda. Lambda, we know momentum relation with lambda. Relation of momentum with lambda, we know. Another thing, whenever there is a decay or whenever there is an explosion, one part disintegrates into two and moves. This is a very, very common condition in our examples of moment conservation. You have seen the examples of gun and the ball coming out of it. There is other examples of explosions when the particles just fly away and their moment remain a constant. Simply here we know that if 1m goes in one direction, 2m has to go exactly in the opposite direction. And what is same for them? P, momentum. So 1 is plus P, 1 is minus P. The sum is 0. Why the sum is 0? Because this 3m was having velocity 0 and its momentum was 0. The momentum of this particle was 0. Therefore, after the explosion, when the two are moving, their sum will also be 0. That's why we are taking up momentum. We also know by the knowledge of physics that wavelength, material wavelength is related to momentum. How it is related to? The answer is P is equal to h upon lambda, where h is Planck's constant, lambda is de Broglie wavelength, and P is momentum. This we have studied, momentum is involved. This we have studied, momentum is involved. So we will work with momentum. We know momentum before decay is equal to momentum after decay. Now here is equal sign. Momentum before decay. This will be equal to how much? According to this relation, this should be equal to h upon lambda 1. and according to moment after decay. Sorry. Momentum before decay. This was not moving. This is before decay. So this was not moving before decay. So momentum was 0. Now what is momentum after decay? After decay there are two particles. One is having momentum P, which is positive, and this P is equal to h upon lambda 1. Why? The ratio of the particles 3 minutes to having non-zero velocities. Okay, the ratio of de Broglie wavelengths, this, their velocity may be different, their wavelength may be different, may be same. So 0 is h upon lambda 1 and plus the momentum of second particle. Momentum of second particle is negative in sign, and if we get the relation with lambda, it is h upon lambda 2. Lambda 2 is wavelength of the second particle. Okay. Here you may say that this is having velocity v1, this is having velocity v2, then this momentum is mv1 is equal to 2 mv2. Yes, that is there, that is correct. But in our question, what are they asking? They are asking about lambdas, not velocities. So for momentum we have a relation h upon lambda. For momentum we have a relation m upon v. It is our choice what we choose. And what we choose, what is asked? They have asked about lambda, so we choose this. We do not choose this. So for the first particle we have taken h upon lambda 1, and for the second particle we have taken h upon lambda 2, but the direction is reverse direction, so it is minus. Now we'll transfer it on this side, so this will be h upon lambda 2 is equal to h upon lambda 1. H is cancelled, take it here, and this is lambda 1 upon lambda 2 is equal to 1. Do we have such option? That means lambda 1 is equal to lambda 2. Is there any one? Okay, none. Right? So our answer comes to be 1. Let me see whether this answer is correct. Yes, this answer is correct. So half, 1/4, 2 and none. None. This is the right answer because lambda 1 is equal to lambda 2 for both of them. And this is perfectly correct. Okay, next question. A potential difference 10 to the power 3 volt is applied across an X-ray tube. The ratio of de Broglie wavelength of incident electron to the shortest wavelength of X-ray produced is this. We know that on a metal, when we apply potential difference, then the electron strike it and X-ray is produced. The electron which is moving towards the metal is having a wave that is known as de Broglie wave, that is material wave. Okay, that material wave has got a de Broglie wavelength for electrons. We know that de Broglie wavelength, this is given by h upon p. P is momentum. This is de Broglie's wavelength of the electron which will strike. The electron will strike and there will be X-rays. These X-rays is a radiation and it is having a wavelength. That is wavelength, the shortest wavelength. We know the formula for that shortest wavelength in the chapter of X-rays, we have studied it. And this lambda of X-ray, I will write it lambda x. shortest wavelength of lambda, and for this we have a formula hc upon kinetic energy. This is lambda shortest. Okay. Now what we have to find? We have to find is the ratio of lambda for electron, de Broglie wavelength of electron, and lambda for X-rays, the ratio. Okay, if we want to make the ratios, then we should have the maximum terms in such a way that we are able to cancel them, or we should be able to put the values. The values given are potential difference, which gives energy to electrons. So we would like to convert them in the terms of potential difference. Also, we know the value of E upon M, that is given to us. We know the value of charge on electron E. So our comparison should consist of either V or E upon M, because these values are known to us. So we try to convert them. Okay, let's convert them. H upon P. Now P, here it is KE, kinetic energy. Kinetic energy is equal to potential energy for any electron. P has a relation with kinetic energy. The relation with kinetic energy with P, we know it very well. Kinetic energy is equal to, let us write it, K. K is equal to half mv square. This is equal to half m square v square upon m, right? This is equal to half, this we can write as p square, momentum square, upon m. This 2m we transfer on this side, so this is 2km. 2km, that is equal to p square. So P is equal to root 2 kinetic energy into mass. Now this kinetic energy of an electron is transferred from its potential energy. When an electron moves in a tube, then initially we give it a potential difference V. It has an energy V into E, and when it goes here, it develops velocity. It has kinetic energy. That kinetic energy is equal to potential energy what was here. So what was that potential energy? That potential energy is V into E. So this we can very well write as root 2 VEM. This is P. This P we put here because V value we know, E value we know. So this is equal to H upon root 2 voltage, electronic charge, mass. Okay, let us stop here. Now we go to lambda for X-rays, Hc upon kinetic energy. Now here kinetic energy is again, we can convert into Hc upon V into E. Okay, this is lambda x. Now this lambda x we have converted V into E, and now we have to compare the two. If we compare the two, then this is lambda de Broglie, lambda X-rays, this is equal to H upon root 2 VEM upon Hc upon VE. This is our formula for shortest wavelength of X-ray produced. This we have done in the chapter of X-rays. Okay, this is equal to, H is cancelled, so we have here 1 upon root 2 VEM, and this will be multiplied by VE upon C. Okay, now VE can be written as square of root VE, and this we can combine. This will become root of this way. This will be root of V square E square upon 2 VEM into 1 upon C. Here 1 E is cancelled, 1 V is cancelled, so VE, this 1 V and 1 V is cancelled. So what is the term we get here? 1 V is left, 1 E is left, and here 2 and M. This is to be multiplied by 1 upon C. And now we put the values. What is the value of V? 10 to the power 3. What is the value of E upon M? Given V upon M, 1.8 into 10 to the power 14. These two values we put here, take the square root, and then make a cancellation with C, and you will find that this whole thing comes equal to 1. Yes, you can do it. You will find that it has come equal to 1. Put the values, and this will be when. And then we check our options. We find that yes, here it is, C. The relation is 1. Okay, so basically what we have to remember is that, okay, let us make it still short. Lambda for de Broglie is H upon P. P, we remember, is equal to root 2 Km or root 2 VEM. Root 2 VEM, shortest wavelength of X-ray is given by HC upon VE. Compare the two, after cancellations, putting the values, it comes equal to 1. This is our answer. Electron, proton separated by large distance. Electron approach the proton with a kinetic energy 2 electron volt. This electron, proton, it has a kinetic energy 2 electron volt. It goes here and goes around it, and this becomes a hydrogen atom. Electron is captured by proton to form a hydrogen atom in the ground state. Then, what is the wavelength of photon emitted? We know this process of producing the light. Electron has got certain kinetic energy. When it reaches here, it moves here, its energy changes. Then there is the difference of energy, it loses some energy. That energy which it has lost, that energy is radiated out in terms of photons, in the shape of photons, and that photon is light. So we can always find out wavelength of that photon. Okay, first we have to find out how much is that energy. So the energy with electron is that was 2 electron volt. We, by our knowledge, we know that this energy in the first orbit of the electron, this is minus 13.6 electron volt. This is from atomic structure. Okay, this we know. Then what is the difference? This energy is negative in the first orbit. This is so, therefore, change in energy. Change in energy means energy released. Energy released delta E is equal to 2 minus 13.6 electron volt. This is equal to 15.6 electron volt is the change. Now this energy, this converts into wavelength. Now we know that if this is the energy released, it will form a photon, a radiation will be there, and what will be the wavelength? That minimum wavelength will be equal to Hc upon V into E. This is 15.6 electron volt, and this value is equal to 12375. This is all known to you. angstrom. So we should remember 12375 angstrom upon 15.6. This is what? Change in energy. This we have done in earlier question also. This is lambda minimum. 12375 into 10 to the power minus 10, that is angstrom. This. So let us solve this, and it comes to be 793.3. 793.3 angstrom. Let us see if this is there. Yes, 793.3. So this is the right answer. Okay, so this we have to remember. What we have to find? Kinetic energy, and this formula hc upon kinetic energy that we have done earlier, that lambda minimum is equal to hc upon kinetic energy in EV. So this, when we convert into angstrom, this comes to 12375, and this kinetic energy here is 15.6, and this comes to this much. Okay, so this is our answer for it. Thank you.